So maybe all 30 more seconds. Just get answers in. You'll have to follow permanent off tomorrow. You want to walk back in? All right. Blocking answers in 5, 4, 3, 2, and 1. Blocking answers now. All right. Anybody's trying to choose 3 objects from 5? Yeah, so I stole the pen for the board. There it is. What's the calculation we're doing here? Oh, yeah, if I choose 3. I choose 3. I have 5 objects. I'm choosing 3 of them. And how do I do this calculation? Five factorial divided by 3 factorial. Technically 5 minus 2 factorial, but this just becomes 5 factorial over 3 factorial over 2 factorial. Or 3, and it becomes everything. So we do this. This is going to be a 5 times 4 divided by 2. 10. Because and was I saying I am permutating these 2 choices that I make. So order does not matter. So if my objects were A, B, C, D, and E that I was choosing, and I'm thinking of the easiest thing for me, maybe just because I'm a mathematician, I deal with steps all the time. I'm thinking about 3-element subsets, which are the ways I can choose 3 elements. So I know the set A, B, C be the same thing as PBA. It's part of the reason why I can't just apply multiplicity principle here. Yeah, it started to rain on us. All right, so the answer to today's daily quiz is 10. I'll admit I tried to. Well, I guess black sign show up on the black, but it's saying it was obvious. It wasn't, but I was trying to at least give you a hint. All right, what questions I got for you? Right. So, common factors. Break it down. There's probably a great explanation due to the fundamental theorem of arithmetic. You know, at least always. Let's see if I can get more like words this. Actually, let me do it on the iPad. We'll show you the recording as well. Do that in a second. I got to share screen anyway. Up there? Yeah. Aren't you all so glad to be inside? Yes. Right now. All right, and choose R n factorial over R factorial times n minus R factorial. And we're going to assume, just for the sake of this argument. We're going to call without loss of generality. We've assumed that just r factorial is the bigger of the two numbers. Probably this decision process that we're going to make is going to follow exactly the same, even if n minus r was the larger of the two numbers. So we kind of make this statement saying, instead of having to repeat myself twice, understand this is just one assumption, but it's going to be symmetric otherwise. Since I know without lots of generality. So let's see. We've never actually done this before. But how we know, right? N factorial is going to be greater than r. Although I'm writing green. And particularly, n is greater than r. Then we know this is going to be n times n minus 1 times n minus 2 all the way to n minus r plus 1 times, I guess n minus r factorial is a better way. I go all the way to r factorial. I'll just write through that. Let's just go r plus 2 times, whoops, times r plus 1 times r factorial, right? Because we saw even in, let's say, 5 factorial, that's the same thing as 5 times 4 factorial, or 5 times 4 times 3 factorial, right? So then I'll have that r factorial cancel out. And don't worry, you won't be quizzed on this. But then what does that leave me with? And I guess this is just what give n r divided by n minus r factorial, and you could probably go through and make an argument that says if you look at the prime factorization of any of these, it's got to show up here as well. I've never actually thought of that question before. That's a great question. Because it will, right? Yeah, which means you'd have to show the factors in the numerator, not necessarily the numbers themselves, but the factors appear in the denominator as well. Or you have to show that the numerator is some multiple of the denominator always. That'd probably be the way you want to go about it. But good question. What other questions I got from? That's not necessarily satisfying. But all right. So what was the last thing we did on Wednesday? And it's proof for a theorem, and kind of what is the theorem trying to say? Technically, yes, and it was motivated by that example of 547, right? So we said, okay, well, if I have 52 objects and I want to choose 5 of them, we found out that it's the same calculation as if I said if I had 52 objects and wanted to choose 47. And what was the little logic we had to do to kind of justify why that was the case? Well, if I'm choosing 5 out of 52, that means how many am I not choosing? 47, right? Or if I'm choosing 47, then how many am I not choosing? 5, right? But when I still break it down, those are still choices, right? I'm just choosing whether to include or choosing to exclude. So we can always change our perspective, and this is one of the fun things about mathematics that can be difficult sometimes when we're first doing it is how can we change an expression? Right? That same concept, and what we said, it boils down to this calculation. We don't have to prove it necessarily conceptually, you can do it straightforward by the formula, right? If I do n choose n minus r, well, n minus r just became r, so we had r factorial. And I just had to make the observation, well, this is the same calculation as n choose r. But it gives us this way that we can start changing perspectives depending on how we want to talk about things. But also, this idea of choice leads into something that is really powerful, especially for a lot of the algebraics. And you actually bring into this a lot. And part of the reason why I like still presenting the binomial theorem, even though I need to find applications for it outside of math, kind of stuff inside, we'll see why in a second. It still just shows you where this idea of choice can still appear in random places, or what seemingly random, but it's all about your perspective. And I turn this into a choice problem so that I can use stuff like this. So what the binomial theorem states, let x and y be variables. Let n be a natural number. I just want a reminder, n can start at what? What's the lowest natural number that we have? 0, and then 1, 2, 3, 4. Then I take a binomial, such as x plus y, and raise it to the nth power, and I wanted to expand that out. This is going to be equal to the sum from I equals 0 to n of n choose I and x the n minus I and y to the I. So I know exactly what the coefficients are going to be if I'm expanding out this type of binomial. So before we actually prove this, we can actually do 2 quick examples, just kind of explain, see what's happening. And what I want you to do is figure out where is choice coming into play. I can guarantee you, in the sake of my theorem, I'm telling you you're choosing something, right? So where does choice come into play? Well, let's start with a simple one. X plus y, let's do squared. What would this become if I expanded it out? X squared xy plus y squared. Because when I look at this expansion, x times y times x plus y, I think I might have accidentally put x times y. X plus y times x plus y, when you're distributing and kind of, it's not bad that you learn the word term FOIL, that it limits you because it only works with 2 sets of binomials. Really what you're doing is distributing, right? You're distributing my first term to everything in the second, you're distributing my second term to everything. So I'll have the x times x, I'll have x times a y, I'll have a y times x, a y times, which is where I get my 2xy. What was that? I just want to be included.
You see the way you should be able to see.
Oh, yeah, absolutely. I'll get back to it. But yes, that should be what's good. Point is, you're distributing, right? I need to say x goes with y. What happens when I do x cubed? X plus y cubed. Well, again, this is just x plus y multiplied by itself 3 times. How does this work? So one thing I could do is definitely, and probably what you're taught early on in algebra, right? Is to say, well, I already know what x plus y times x plus y is. I'll substitute that in and then just multiply by x plus y. And that's very, very valid. That's going to limit our perspective. The distributive property just says, I take this x plus y, and I'm going to choose what else to multiply by. I have to choose this x to multiply by one of these two terms. And then I also have to choose it again once I've chosen that, figure out another term to multiply by from this third binary. So one option is I can do x times x times x, leaving me with 1. X cubed. Well, I don't have to do just x times x times x. I could say, okay, well, I choose an x to multiply the first two, and then the third one could be a y. So I have an x times an x times y, or an x squared plus y. That's not the only way I can get an x squared times y term to appear, right? I could do an x from the first term, choose a y from the second, and choose an x from the third. Now I'll generate another one. And what's another way I can generate an x squared plus y term? Y x x. And so how many do I get in total? Yeah, and we'll see it down here. 3x squared times y. But then I'm not only saying, okay, well, what if I now want to choose, instead of one y in any of these combinations, only one x? So I choose an x from here, a y from here, and a y from here, multiply together. And how many different ways can I do them? Yeah, so one way I can get two y's and an x, say, take a y from here, take a y from here, and then take an x from here. So that's going to give me one. What's another way I can choose to get a y squared times x term out of that multiplication? Yeah, I can say choose an x from the first term, and a y from the last two. There's one more way. Y x y. It's technically xy squared plus xy squared, giving me 3 of them. And then my last option is to just choose 3 y's from everything. There's only one way I can do that. I get 1 y cubed. So overall, this just becomes x cubed plus 3x squared y plus 3xy squared plus y cubed. Everyone's starting to see where choice is coming into play. We can quickly now, if we start to see this pattern, even go, what is the expansion of x plus y to the fourth power? So I have x plus y times x plus y times x plus y. So my first thought is, how many ways can I go through all of these 4 binomials and multiply 4 x's together? Yeah, just in one x to the fourth term. And then how many ways can I go through this expansion of 4 binomials and get 3 x's and 1 y. So x, 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 y, x, 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 y, x, x, y, x, x.
So they will X this way more.
But where is that 4 coming from? Well, I had 4 binomials to choose from, and I wanted from y. All right, now if I want 2 x's and 2 y's. Would it be 4? So I can say, let's just do it from perspective of y's, right? My 2 y's come from here, that's one option. 2 y's here, so 2. 3 options. 4, 5. 6, 7. If I just count them all out. But again, I am going through and I'm choosing how I'm going to select 2 y's to multiply by out of all 4 of those targets. So really, that's just breaking down to 4 choose 2. So if I can do that calculation real quick, just because I see some faces. 4 factorial over 2 factorial times 2 factorial. Going to boil it down to 4 times 3 divided by 2. And 4 times 3 is what? 12. 12 divided by 2 is 6. How many ways can I choose 3 y's from those 4 binomials to multiply together? 4. Because I can also turn around and be, what's the way to not choose, or to only choose 1 x, or so to not choose a y. So 4 choose 1, we're going to give me 4. And how many y cubes? Just 1. Uh, 4. Why are my exponents off there? No, wait. Well, that's not supposed to be what I say. I'm supposed to say yes. And that's the way to pay attention. But even so, with the x to the 4th term and the y to the 4th term, those are still choice, right? For the x to the 4th term, how many y's am I trying to choose? 0 y. Or choose 0 times x to the 4th, and then technically y to the 0th power. But anything to the 0th power is 4. Let me maybe write that a little bit farther to the right, so I can write that y to the 0th term. Or choose 0, x to the 4th, y to the 0th power. And then if I go through that last one, that last term, I'm saying, how many ways can I choose 4 y's from 4 objects? So it's 4 choose 4 times x to the 0th power, y to the 4th power. But because of the distributive property acting on these binomials, it just boils down to choice every single time. How many x's am I choosing to multiply together? How many y's am I choosing to multiply together? In either way, I can always get that expansion. And with this understanding, we can now finally do a proof of that binomial theorem. And no, we're not going to do it by induction. This is going to be more of like a concept proof, kind of what we're working for. So this is not a full-on rigorous proof, just an FYI.
When you talk about choosing, is that for choose for or
Yeah, 4 choose 4. I'll rewrite that. or choose one. So if I take that binomial, raise it to the nth power, this is just x plus y, x plus y, x plus y, and I keep doing this multiplication n times. So when I go through this expansion and I'm trying to figure out how many terms I have, or x to the n minus I times y to the n. We have determined, I'm really going through and saying of these n different binomials, how many y's am I going to try to use from each of them, or choose from each of them? I total. I'm going to make I choices from each of those binomials of the term y. And just a nice little caveat with I just being somewhere between 0 and n. Well, I forgot to turn time off. Let me take another sip of coffee. I don't support Ryan's 3 cups of coffee in the morning. Maybe I'll make a little bit more.
I think you should have 3 cups of coffee.
No, you don't hate me. I trust in you hate me. My ADHD tendencies would shine brightly, and that's not. So, to generate it, we need to choose J, Y's. And we're to write that J is a number, Y is a term. Out of the total of n Y's. Thus, there will be, and choose J, x to the n minus I, or no, not J, let's choose I, x to the n minus I times y to the I terms in the expansion of x plus y to the power. Therefore, if I go through every possible option of I, starting at 0 all the way up to 1, and I add them all together, I'll get my binomial expansion. So for every possibility of I, starting at 0 and n, we add those choices together. You can see that we generate what is called Pascal triangle as well, or the binomial expansion. So really quickly on the proof though, what questions I got? Hopefully this is just stating in general terms what we kind of established in those finite cases. When we squared it, cubed it, and raised it to the 4th power. Well, we can actually use that binomial theorem in other ways. To prove some other concepts. So for example, we're gonna have this corollary. So corollary is a theorem on its own, but its proof is going to involve just a simple application of the binomial theorem. And what this corollary says is, let n be some natural number. Then, if I sum up all of my choices, we use now. I consider n choose 0, add it to n choose 1, n choose 2, all the way up to n choose n. That total sum, if I add up all possible choices I can make of n objects, each instance, it'll just be 2 to the nth power. Anyone see how the binomial theorem comes into play, though, to prove this? Pat? Or what are you picking up on?
So it's kind of similar to, very specifically true. I implement it's the terminology like 4, 2, 0, is it?
Yeah, so if we took it back to that one example, right? So let me write this in green again. What we're saying is 4 choose 0 plus 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4. This will actually be the same thing as 2 to the 4. Well, 4 choose 0s we saw was 1. What was 4 choose 1? 4. 1, 1. Well, 2 to the 4th power is 16. Do I have 16 added up on that left-hand side? Yeah. That is a valid equation. If I do it for that trinomial and I extend it out and I add up all those coefficients, I'm going to see they add up 8. It would be a 1 plus a 3 plus a 3 plus a 1. Even if I do this for my standard x plus y quantity squared, if I take my coefficients 1 plus 2 plus 1, it gives me 4, and that's the same thing as 2 squared. And here's how we use the binomial theorem to prove it. Wait, what's up?
I don't think the way you could also use the like.
Oh, when you put a number over number, you want to, yeah. All this proof requires us to do is to be clever about the choice. We're going to let n be a natural number. And by our binomial theorem, we're going to have 2 to the nth power. Well, how can I rewrite 2 to the nth power so that I see a binomial raised to an nth power? Plus 1. I can view this as 1 plus 1 raised to the nth power. So then my first variable, i.e. the x, is now just a 1. My second variable, y, is a 1. If I go back to my binomial theorem, if I raise 1 to any power, what am I going to get? 1. So all those xy terms that I see in that multiplication will just end up being 1. So by my binomial theorem, when I expand out this 1 plus 1 raised to the nth power, It's going to be the sum of from I equals 0 to n of n choose I times 1 the n minus I times 1 to the I. But again, 1 to any power is what? 1. If I multiply by 1, you can never change anything. So I'm just then left with the sum from I equals 0 to n of n choose I. What questions do you have? All you gotta do is change your perspective and things just open up and the world will expand. Next up, which is again dealing with choice and related to binomial theorem, something called Pascal's identity. And if you ever heard of Pascal's triangle, this is what generates it. So we're going to let n and k the elements of the positive integer. So we're starting at 1, going up 2, 3, 4, and so on. And we're just going to make sure that n is greater than or equal to k. Then the calculation of n plus 1 choose k can be broken down into 2 separate calculations. N choose a minus 1 plus n choose k. So I want to choose a objects from n plus 1 distinct objects. The same thing as choosing k minus 1 objects from n objects, adding it to the number of choices I get. We're choosing a objects from n objects as well. So, same preamble that we have in our theorem, let n and k be positive integers with n being greater than or equal to k. And what we're going to do, I'm going to say, suppose that capital B, you're good, is a set containing n plus 1 objects. Or said differently, the cardinality of the set B is n plus 1. And then we're going to define a set D to be that set B minus a particular element. Of B. So essentially, I'm setting this up to where I can make choices from n plus 1 objects, i.e. choices from the set B, or I can make choices from the set D, which has 1 less object. Oh, there's my Pascal's part. copy, delete it, and we'll show it later in a second. So, we know there are n+1 choose k ways to select or to choose, not ways. There are n+1 choose k subsets of B that contain a+1 elements. A+1, why am I, oh gosh, I'm sorry, y'all. Should be k on that. So let me repeat that. Maybe it's at the bottom. We know that there are n+1 choose k subsets of B that contain k elements. So I'm going through the set B and I'm making subsets size k, k elements to choose from out of n+1. But when I think about those subsets of B, they can be classified in two ways. So if I go and investigate each of these subsets of cardinality k, well, the first case is that that subset is k-1 elements of my set D unions with that set containing that particular element B. When I've chosen these k elements from my larger set B, I have a choice of saying little b was in there, which means, and the rest of them have to come from my set B. And I define just B everything else. And that means that there had to be k-1 options chosen from D. But what's the second case? Well, first case is that little b is in the subset. And little b isn't. If little b isn't in that subset, then everything came from what set? D, even dog. So for that first one, how many ways can I choose k-1 elements from the set D? And choose k-1. And then for whatever those choices are, all I'm doing is saying I'm tacking on an extra element into each of those sets, which is that element B. Is that going to change up the number of choices that I make? No. They're going to have the same number of choices. So for that first case, there are n choose k-1 ways that can happen. What about for that second case? How many ways can I go through and choose k elements from the set D? It won't be n+1, right? What's the cardinality of my set D? Yeah, it would end up being n choose k because my set D was created by taking a set with n+1 objects and removing one. So it would only be n. And when I go back to these two instances, Are they disjoints? Can they happen at the same time? So if the subset is only in the set B, that means that it absolutely cannot contain what element of the bigger set B. The little b, right? This first case requires my subset to contain what element? Little b. So we get a dichotomy here, right? You either contain the element little b or you don't. And those are two disjoint instances. And if I'm considering a disjoint sets, well, the number of subsets that I can choose for the first one, or the number of subsets that I can choose for the second one. When I turn that into mathematics, that or statement becomes a one. Figure that out. Plus A or B's. Cardinality of A or B is the same thing as the cardinality of A plus the cardinality of B. With 1 and 2 are disjoints. Then I know the total number of subsets that I can choose of k elements from n plus 1 would be equal to my first instance, which is n choose k minus 1, plus my second instance, which is n choose k. We'll try to leave that out. I see the time, so I'm not going to spend a lot. This is what leads to what is called Pascal's triangle and Pascal's identity. And you can build a triangle where each row is 2 to a 0th power. It'll sum to 2 to a 0th power. And if you take any two entries and add them together, you can get one row. Or if you want to think in reverse, if I take an entry, I can split it up to 2 separate pieces of bottom. We kind of get this triangle look of calculations to appear, which is where something like Pascal's triangle comes into play, and how it's generated. All right, so that's it for today. I will see y'all on Monday. We have everyone here. We got everyone here. So while you're backing up, midterm next week is going to be take home. Okay. So that means we'll not be meeting in class. I'll make sure there's an announcement on Blackboard just to remind you. Right? But we'll not be meeting. You're going to use that class time instead. You're taking the midterm, and if you need more than 50 minutes, you won't take any time outside of it. All right.
So it's gonna be on Blackboard?
Yeah. So it'll be a kind of like how we have our written homeworks on PDF for you. You download it, write all the questions, answer them, take your photos, turn them into a PDF, and upload.
Is this gonna be for the next class too?
Maybe, I don't know yet. I'll tell you about this one. It's definitely going to be